So I want to talk about Opetopic structures. We will see what that means in a second. The work is really related from an abstract way to see syntax, but there is no time to talk about syntax in 30 minutes, so I will skip that and really concentrate on the algebraic aspect. So in a sense, what I'm going to do is to provide an algebraic approach to understanding how we generate higher dimensional structure as you understand it in higher dimensional category theory in the context of Opetopic sets. So really in these talks we are going to generalize special kinds of shapes that are interested in higher dimensional category theory. They are called Opetopic. And they are crucial to defining Opetopic sets, which is the first level before you start defining more sort of interesting higher dimensional structure like categories or categories with algebraic structure and so on. The thing to have in mind is that these Opetopic structures are really of the form of a multi-category. So your maps are always many to one. So it has been studied by many people, starting with Baez and Dollar, and the approach that I'm taking, really I'm indebted to Marek Zawodowski, who unfortunately passed away recently, because he was the one that studied these structures with Sawell and thought that it would be related to work that I've done. And in fact, after he asked me this question, the material of the talk came about. So, as I said, these Opetopic structures, or Opetops, they are going to be generated in a multi-categorical sense, so not globular, as we've seen before. And so the cells that we are interested in are always many to one. So, implicitly, at least if we see at the very low dimensions, we see a list structure. So, a two cell is going to be from a list of composable one cells into only one cell. This list structure is crucial, and in fact is going to permeate over and over all dimensions. What we need to do is really understand in which sense we are dealing with list structure. That's one part of the talk. Okay. So now we go one dimension up. So I'm going to motivate the structure, the algebraic structure I'm going to look at by drawing some pictures. So now we have a 3-cell. This 3-cell goes from many 2 cells that have to be appropriately pasted into only one 2-cell. And again, I claim that this is some kind of list structure of 2 cells into just one 2-cell. Okay? And so we need to understand in which sense this is something from a list structure into one cell. So the way in which you see this done many times in higher dimensional category theory is by combinatorially reducing to trees. So the 3 2 cells that I have up here, they are now encoded as a tree with corollas corresponding to each 2 cell from, in this case, 3 to 1, in this case 2 to 1, and in this case 2 to 1. And the operation of putting these things together is algebraic structure that you have, and typically called leaf grafted. Okay? So I have 2 trees that are grafted into this corolla of arity 2. If you think algebraically in terms of operators, so you have an operator of arity 2 operations of arity respectively 3 and 4, and they are substituted into this operation of arity 2 to give me a new operation of arity 5. Okay. So the first thing I want to stress is that this grafting, even though we are performing it on tree, it's really list structure. Okay. So in fact, what we are dealing with is list objects, or in the sense of Max-Kelly algebraically free monoids. Okay. These are initial structures with a unit and an action that are initial in the parameterized point of view. Okay. And this list object will be crucial in what I'm going to do later on. Okay, so how can these trees are actually list objects, or in fact they correspond to list structure? So here is an intuitive way to do that. Think of F as end-of-functor, say, on sets for some signature of operator, say, of finite linearity. If you look at the free monad on it, or the least object on it, you see that this exactly describes as some kind of tree structure. So a term is either something that comes from your variables, or is an operator applied to, again, terms. Okay. So I want to see these trees really as coming from least object. And the operation of grafting is nothing but substitution, okay, as derived freely from the monad structure. Okay, so now we want to try to understand what the force cell should be between these opetops. Okay. So we have a 3-cell. Now here I should have something like this from many 3 cells to one 3-cell. And so it would be something of this kind of sort. Okay. So I have a kind of a tree structure, but again, I want to emphasize it's a least object structure of 3 cells, from which I go to via a 4-cell to a 3-cell. Okay? And all these, they have to be compatible in suitable form. And this compatibility now makes you recognize that there is extra structure that we are not seeing until this point. So let me show that. So we need to ensure that these things are compatible, and in doing so, we need to understand that we are able to kind of plug these 3 cells in this one so that we obtain that one there. Okay. So there is, in this higher dimensional category theory, and in these opetops, and in all sorts of higher dimensional structure, another kind of composition. And this is vertical one. Okay. And I can depict it in this form. So this tree that we saw before, that was obtained by grafting, actually now can be replaced by another tree of the suitability. Okay? So now we have another notion of composition, which in the opera world or in higher dimension is called node replacement. So you have a node and you can't replace it by a whole tree. Okay? So we see that to understand this, the structure at a higher and higher level is quite complicated, but we have selected 2 operations of composition. One is of grafting, another one of replacing. And the interesting thing is that they are compatible with each other. So here I have a little example which shows that if I graph, say, these 2 trees into this one, that's one thing I can do, or I can replace these nodes by bigger trees and then grafting. You see that the operation should give you the same thing. Okay? So we're working with 2 notions of composition compatible with each other. For the purpose of a opetopic structure, or multi-categorical structure, we need to understand in which context we are and to state this compatibility. And so that's what I'm going to do next. We also know this from 2-dimensional category theory, like the interchange laws of 2 categories of the same form. It's a compatibility between vertical composition and horizontal composition. Okay, so now we need to analyze horizontal and vertical compositions. To do that, the first step I'm going to do is to regard composition as generalized monoidal structure, monoid structure. It's going, different notions of composition are going to be monoid structure for different notions of tensor products. Okay. And what I need to do is to state in which sense these notions are compatible. So here is what's happening in this case. We have 2 notions of composition, so 2 monoids on the same, on one object. With respect to 2 different tensor products. Each of these tensor products model different kind of composition, as I just said. And what we need to do is to somehow explain how they interact, in the sense I explained below, of commuting with each other. So what's the algebraic framework for doing that? It will involve some kind of interchange law, okay, that is is going to be stated by a compatibility condition. So what setting we're going to look at now? So there are many settings in which you can do this. So I have done it previously in the context of syntax. This work is about Opetopic structure in particular from the combinatorial point of view, which I'm going to look at in the second part of the talk. You can also do it for a strict higher category theory. You will use different kind of structure. This will give you notions of internal categories that are actually defined by induction rather than straightforward given for all n. Okay, so what is the algebraic structure now that axiomatizes these notions of compositions that are compatible with each other? Okay. So as I said, I'm going to identify substitution structure or grafting structure or with monoid structure. And now the question is, if I have two compatible monoid structures with respect to some tensorial strength, what does it mean to be monoidal in that sense? So let me just explain what we need. So we need to work with categories that are have a near semi-ring structure. Okay? So a near semi-ring category has two tensor products. They may or may not be skew. In fact, everything would work with a skew. In the examples, they are not. And these tensor products, they happen to be compatible with each other in the sense of having a tensorial strength. So I have the dot tensor product has a tensorial term with respect to a star tensor product, and that is the extra structure of a map that allows me to distribute the parameter set in each of the arguments x and y in a suitable coherent form. So every Cartesian category is a near semi-ring category. That's the most straightforward example. It's not the most interesting one, and I'm going to show you how we generate categories with this algebraic structure. If you want kind of a formal definition, really what we are looking at is as pseudomonoids in a suitable two category, but never mind. You can also write down the coherence by hand. Okay, and so what is now an object in a near semi-ring category that has two compatible substitution structure is in fact a near semi-ring object. Okay, so a near semi-ring object is an object which is has two monostructure as before, and now because I have the near semi-ring structure in the category, I can state the compatibility condition. Okay, so if I do one operation and then the other one, modulo the distributive or the tensorial strength, I can commute them. Okay, so what I'm in any monoidal category, the monoidal category is a framework in which you can define monoids. Well, a near semi-ring category is a framework by this kind of microcosm principle in which you can define near semi-ring objects. Okay? And the way in which higher dimensional structure is derived in higher dimensional category theory, it involves this construction, that's, at least for Opetopics. And that's the point of the talk. Okay. Okay, so let me now give an example, and this example I'm going to use later on, of these near semi-ring objects. Okay. They appear all over the place as soon as you have exponentiation in your category. So take an arbitrary monoid M in some Cartesian closed category. Now look at the endo-home from M to M. This is not the endo-home of monoid homomorphism, it's the full home. Because you take the full home, now you have two monoid structures on this. The composition structure, but also the pointwise monoid structure that you get from your monoid. Okay. And this is not a semi-ring, because only one of the distributive law holds, and that's what makes it a near semi-ring. So we have the the composition structure, the pointwise structure, and the distributive law only of the circle over the star. And not the other way around, again, because we are not restricting the maps from M to M to be monoid homomorphism. And this example I'm going to use in a bit in the context of, well, in a particular Cartesian closed category. Okay, so near semi-ring categories are the universe of these curves. We're talking about, well, algebraic theories that are star monoidal but tensor strong or dot strong. Near semi-ring object is one particular such algebraic theory. In fact, there is a general notion of compatibility of algebraic structure with some kind of monadic structure that we have developed with Philip Savit, somewhere there. And this is just an instance of that theory. Being an instance of that theory, in fact, we can get some results for free, and here you see the prominence of this list object. So, in a near semi-ring category with enough structure, as typically you have in examples, you can actually give a quite explicit description of the initial near semi-ring object. And it is nothing but a list object. It's the list object, well, with respect to the star structure over the unit of the dot structure. Okay, so near semi-ring, initial near semi-ring objects, they are really syntactic structure, and they are nothing but certain kinds of list objects. And I'm going to generate these initial near semi-ring objects, and these are going to be the gadgets that describe higher dimensional cells, starting from the specification of lower dimensional ones. So these I'm going to do in the bicategory of generalized species, a generalization of a Joyal species. An AB species is a profunctor of this form from the symmetric monoidal completion of a category to another category. You think of the elements in such a profunctor, such as in a species, as operations. So an element in the profunctor T from A1, AN to B is an operation sorted by A1, AN of type B. Okay? And as such, you can compose them. So the idea is that if I have operations with inputs in A's and outputs in B's, and another one with inputs in B and one in C, then you do the multi-categorical composition to get operations in the composite structure. Okay. I just want to convey the idea of what's going on here. We have identities, so identities are just wires in your category UR, and this forms a bicategory. In fact, it's not any bicategory, it's a Cartesian closed bicategory. And the Cartesian closure is crucial for the construction I'm going to do in a minute. So to explain a bit in which sense is Cartesian closed, I'm going to describe the product structure. So the product of two categories here happens to be their categorical sum, this joint union. The exponentials, you can imagine, they are of the shape of many to one. The exponential in this bicategory from A to B has to describe many to one maps or operations. So it's many to one. Now, there is a very interesting interplay between global and local structure that I'm going to take advantage of in the construction I'm going to perform now. And in particular, well, as we know in any bicategory, the endohomes are monoidal categories, and this is going to play a role. So let me just say a bit more about this view of global versus local. So globally, we talk about monads in bicategories. You see them as these four. Locally, I can talk about monoids in the endohome monoidal category of an object. Okay? And passing from one to the other is going to be important. Now, these monads in species, or equivalently monoids in the endohome, they are generalizations of symmetric operas. They are generalizations because here A may be an arbitrary category rather than a set of colors, as we typically do there. Intuitively, the operation of from T composed with T to T takes formal composites of operations from T and assigns an actual composite. And as usual, the monostructure just says that this is associative and well, has a neutral element. Okay, so in the last 3 minutes, I'm going to explain this construction. It's purely algebraic. It's a construction that tells you, given an opera, okay, how you, that describes certain notion of operations, how you generate a new opera. The new opera is an opera between the operations of the previous opera themselves. So given an opera T, colored by things in A, I'm going to generate a new opera, so a set of operations colored by the operations of T. That's the category of elements of T. Okay? And this explains how certain operations in one dimension have to be taken a dimension up to the next one as being operations between operations. This is the Weiss-Dolan construction called plus construction or slice construction. What I'm doing here is expressing it completely in pure algebraic form internally to the bicategory of species. So how does this go? So first of all, I take my opera on A. It's a monoid in the endohome of species. This monoidal category sliced by a monoid gives me a new monoidal category. This is standard category theory. So now I have a new monoidal category. This monoidal category, because I'm slicing a presheaf category over some presheaf, I can see it itself as a presheaf over the category of elements. And now we see how we pass from looking at category A to looking at the category of elements of T, which is nothing but the operations of T. Okay. Okay. Once I have done that, okay, because these two categories are equivalent, I get the monoidal structure on presheafs of the category of elements. Okay, straightforward. Okay. Okay. Now there is a bit of work we have to do. This monoidal structure actually happens to be analytic, okay? Which means it can be internalized itself in the bicategory of species. And that means that this monoidal structure, in fact, I can see it as a pseudo-monoid in the bicategory of species. So now I have a pseudo-monoid in a bicategory that is Cartesian closed. So I can consider the endo-exponential in this Cartesian closed bicategory. This gives me a pseudo-semi-ring object in species. It has two notions of composition, the one that I inherit fiber-wise from T, and the one that given by composition of the exponentiation function. And okay, so if I externalize this, what I'm saying is now the home category from the category of elements of the opera T to the opera T happens to have near semi-ring structure. Okay, and now one more step. What is the plus construction? Is nothing but the initial near semi-ring object with respect to this near semi-ring structure. And this is how you generate higher dimensional structure starting from one opera on some set of colors to an opera colored by the operations of the initial opera. Okay? And this is essentially what's happening in the plus construction. And now, once I have done this, I can restart the process. So I take A to be my category of elements, T to be T plus, and restart. And this is how you generate higher and higher dimensional structure. And in particular, and I conclude here, the example of Opetopic comes from the most simple opera you can imagine. Thank you very much.
Yeah, first, thanks very much for the nice talk. I was wondering at what step in this algorithm at the end the sort of combinatorics blossoms out for operas and sort of explodes. Is it
yes,
internalization? Is it the initial object? Like, where?
So there are two things. Of course, I present it in all abstract form. This abstract form corresponds completely to calculations with these operas that actually can be described formally even in the calculus of coherence. If you look at this calculus of coherence, you see very precisely all the manipulations that are typically done when explaining this kind of thing using pre-grafting and stuff like that. So that's one place. And the other place in which, so here when I said that T plus is the initial one, being initial is intuitively being a syntactic form. And that's where the trees and all the things that you see combinatorially really appear in that construction. So this construction it involves computing a list object with respect to these tensor products, and that's precisely where it appears.
Okay, great, thanks.
But that I hear it all the way because here I wanted to emphasize the purely algebraic aspect. I think it's interesting because it explains it well, purely algebraically, but also in a universal form, because this is a universally obtained object. And also it's applicable in other places. Okay, so I apply this in the bicategory of species, but if I find another Cartesian closed bicategory, I know other examples, I can reapply this and discover new versions of this construction.
In the original paper by Baez-Golan, they treated it with symmetric operas.
Yes.
And then afterwards, I think Atamin and co-authors treated rather the case of non-symmetric operas. So probably you are closer to the initial Baez-Golan approach.
This is exactly the symmetric case. And this bank, so when I described the Cartesian closed structure, I took the three symmetric monoidal category and category. That's where the symmetry is embedded. That is what gives me the Cartesian closed structure. If I just take the three monoidal category, I get the bicategory that is not Cartesian closed. And so I cannot play this trick. Marek told me that the original Baez-Golan paper has some little mismatch here and there, and it's because of some mismanipulation with the symmetries and so on. So one has to be very careful when you do things non-symmetric.
Yeah. Thanks for the talk, Marcelo. I was wondering whether what you're writing with the integral is to be thought of as a growth and deconstruction in some sense of the operad acting over itself, because that.
Yes. So here I wrote it as the plain category of elements. Now, because I was performing it just over T and on that underlying object of the opera, the question is interesting. If I regard the whole thing as an opera, I'm producing a new one. Would this be a growth and deconstruction? I've not thought about it. Very interesting. Thank you very much.
Well, remember the picture when next time the speaker again.